All right, so we'll talk about some of the observations and a few details about friction. You can see we've got the fact sheet. There's a lot of weird facts that are not necessarily like friction's weird because we have the moving and the stationary friction. They're two separate ideas that just combine from the same concept. So friction basically is just a force that opposes sliding, right? And this is a very important definition in that because it opposes sliding, a lot of people like to think it opposes motion. But the problem is, if we didn't have friction, we also couldn't start moving, right? If I'm standing still, if there was no friction in this room, well, first of all, I would fall down to the ground right away. But also, I couldn't start moving. I'd just be stuck in one place. I need friction to move also. And we can see this with Newton's third law. If I want to start walking, what I have to do is I actually have to push on the floor. I have to push back on the floor with my foot, right? I push back. And then when I push the floor pushes me forward. And so that's where Newton's third law puts this all together. And so it's not that it opposes moving, because I need it to move, but it does oppose sliding of things. And friction, because it's also caused by surfaces, just like our normal force is caused by surfaces, basically the normal force and friction are part of the same force. And we just call this one the parallel component of that force, the force that is parallel to the surface. And you guys have taken physics before. Do you remember what the factors are that affect friction? Sort of, yes. So there's only two things, which is pretty cool. So kind of mass, not quite, but almost. It's related to mass.
Yes. How rough the surface is.
Yeah, how rough the surface is. So like the materials that we're rubbing together. So yeah, the types of materials, and then not mass, but normal force. So it turns out like, well, actually I can demonstrate this with something less dangerous than my iPad. Right? So if I try to push this here, it requires a certain amount of force to move. If I put it like this, it moves without me applying force. But at different angles, it becomes easier or harder. Now, this is a bad example because gravity is pulling. If I try to push it like this way, like this, it's actually easier for me to push when it's on an angle because the normal force is less. So even though it had the same mass, the normal force is what does it. And we do have an equation, but the equation is confusing, which is why we did the lab first. So this is my data, but you guys had similar graphs. So can we describe what's going on here on the left side? What did you observe when we were doing this experiment? And I'll write some annotations on the board here. So yeah, what happened on the left side of this graph and the left side of this graph? What was happening over here?
The object is not moving.
All right, so I'll write that down first. So yeah, it's not moving. It's at rest, same position. And what's the relationship between the applied force and the friction force at that spot?
Directly.
So yes, so the word you're looking for is directly proportional.
Oh yeah, directly.
But not just proportional, because proportional can be like, if this doubles, that doubles. But as Roxio said, they're not just proportional, they are exactly equal.
Oh yeah.
So like when this is 25, that's 25. When this is 50, that's 50. And that was true for all frictions. So when these things are at rest and stationary, we have one equation that says our friction force is equal to the applied force. And so whenever something is stationary, we actually notice that friction is changing. And so if we want to solve for friction, we don't have an equation for this. We actually have to use Newton's first law for this. So we have to set up an equation where the friction equals the other forces and balance them. But that's this side, that's when it's not moving. When it is moving, what do you notice there? Well, so let's start with the same thing. So before it was not moving and at rest, so let's do the same observations. What's happening on the right side here?
Object have a constant acceleration
Usually.
and the friction is also the same.
Right. So I'm just going to say it is moving
It's moving.
because it's possible that we could, like, we could see that this friction level for this one is about 128, or sorry, 118. And therefore, if we pushed with 118, we could get a constant speed also. Right? This one is 70. If I pushed with 70, it would stay constant speed. So maybe it's not constant acceleration, but it is moving, which is a big difference, right? And so when it is moving, you noticed, yeah, that at least for this object, the friction always stayed the same. For this object, the friction stayed the same. So whenever we're moving, the friction, actually, let me write that with black so I keep the same structure. Friction is constant when we're moving. And it turns out that we do have an equation for this. And, well, we sort of saw this. So what happens when we increase the mass? What happened to the friction?
Increase.
It also got bigger. It's hard to tell from this graph, but it turns out if you double the mass, you will get double the friction. And so we actually have a relationship for this one. We can say that the friction force for moving is a constant, and it's pretty easy to calculate. It's the normal force times a constant. Do you remember what the constant is from last year? It's that letter, that Greek letter.
Oh.
That's not O, that's mu.
Oh, yeah, no. I just want to.
Yeah, so having more mass gives us more friction, and having a higher coefficient here.
Friction.
Yeah, exactly. It's the coefficient of friction. So I'll write that here. There's our equation. This is the equation you would see on the equation paper. So yeah, you'll notice that this is the only equation we have this year that has this inequality in it, and that's because of the way that friction changes. So when we're stationary, we have one rule, and when we're moving, we have a different rule, and so that's why this equation is a little bit weird. And I think we're going to spend, like, we're going to do notes here, of course, but then we're going to do just basically practice today, tomorrow. Just really quick for a reminder here. So this little symbol here is the Greek letter mu. That's how it's pronounced. I guess you could think it's pronounced like but yeah, it just says how much do like the two materials kind of stick together when they're sliding. And because it's just a ratio of the friction force divided by the normal force, there's no units for it. So it's just a number and that's it. So this picture, you don't have to memorize this. You don't have to write this down. This is just so we can see some relationships. So you'll notice here's a list of just common everyday things. Don't worry about the dash. Like people in my other class were obsessed with the dash. And I explained it twice and they kept asking, why is there a dash? So they don't listen. But yeah, don't worry about the dash. I just want to see, like, if you look at all these numbers and you see there's two columns of numbers here, do you notice any patterns based on the numbers you're seeing here?
The surface of the material is smooth and the friction coefficient is small.
That's a good observation. Yeah. So like when we have smooth things, like for example, ice on ice, it's a really low number, right? Whereas rubber on concrete, this is like a car tire on the road, right? The biggest number is a 1. And then one more pattern. So we looked at the numbers. Sticky things are big numbers. Non-sticky things are small numbers. What's another thing that you maybe noticed from this? Maybe not. Why are there two columns?
Yeah, I'm wondering where does mu came.
Right. And one side is always bigger than the other, right? So we haven't talked about these names yet. So this mu s,
Oh, I think I know.
oh, what do you think you know?
I'm not sure teacher.
Okay, I'll say it, fine. So this S stands for static. And this K stands for kinetic.
Oh.
Oh, what is those?
There's a two kinds of friction.
Right.
So the values of the coefficients is different.
Right, yeah. So one of them is what we use for the maximum, like the not moving friction, and one is one for moving. So yeah. So for stationary things, we have static friction, and for moving things, we have kinetic. Like the word kinetic is an old word for motion. It's the Greek word kinema. It means motion. So like we studied kinematics in September. That's what kinetic all means. It means motion. That's why kinetic energy, right? Same thing, right? And static, you maybe heard the word static, like static electricity, maybe. So that electricity is electricity that's stationary. It doesn't move from place to place. Like this electricity is not static because it's flowing. All right. So I think we see the observations. That's good. So I have questions here, but we talked about them already. So here's the official notes for today. So static friction, stationary friction, and kinetic friction is our moving friction. We have these two rules. So one says that the static friction, it varies. It changes between 0 and some maximum number. And that's because when we're not moving, the static friction tries to respond to what we're doing. If I push a little, it pushes back a little. If I push a lot, so it always equals our pushing force until we break it, until we get past that pushing force. And what we can measure here is the maximum value. So friction maximum, this is where we can actually use an equal sign, is when we get to the biggest possible value, we can measure what is that maximum possible value, and that's our mu s. That's where the s comes in, times our normal force. So most of the time when we're dealing with this, we will be applying Newton's first law. There's no equation, but we have to use Newton's first law to solve for it if something's not moving. But we can find, like I said, the maximum number. Now, on the other side here, kinetic friction is when, that's not, all right. Well, you guys noticed this already, that it's a constant force. It's always the same number at all times. No matter how fast you're going, how much force you apply, it stays the same number as long as we are moving. And let me just get this out of here. So yeah, if you're a notes person, this is the time for notes. If you're just a person who stares at me while I teach, this is your time to stare at the screen.
So does the friction, the mu show on the paper?
Yes.
Oh.
Now, this, like something like this chart, hold on. This would never show up on the exam because there's no need. Because most AP exams are not about calculations.
Oh.
Now, we do calculation practice in here because I want you to see the different possible ways to use these. But like when it comes to the exam, it's more about the explanations. And like next week, when we're reviewing for the exams, we'll focus more on the explanations. Because I think you guys are actually quite good at the math. But saying, why do I know this? How do I know this? That's the stuff that's challenging for us. So, but for today, we're doing math practice. And tomorrow too. So here's a basic question. I think we'll have time for like 2 basic ones together, and then I have a practice paper with 2 more for homework. You might have time to do it in class today. We'll see how long this takes. So we have a block sitting on the surface. It says the coefficient of friction is 0.3. Now, it doesn't say what kind of friction this is. So if we read the question, though, a 10 Newton force is applied to the block. What is its acceleration? The question is about acceleration. So what kind of friction is this?
Well, kinetic.
Yeah, it's going to be moving, right? So this is our kinetic friction. And so since we want to know about acceleration, this is a force question, so we should draw a free body diagram, just like any other force question. So let me just draw a small one over here. So we have gravity, and force, and it's equal to right and friction. And left opposite. Now, I don't know what it is, I'm trying to shake it. But the question says it's about acceleration. So what law do we need to apply? Second law. Let's do it. So we can say our forces to the right minus our forces to the left equals ma. Because our acceleration is to the right. And now this question is just like every other question we've done. Right? Our force to the right is an F. Our force to the left is friction. But we can replace friction with its equation because it's moving. So we can say this is mu times Fn equals ma. And now we just put numbers in, right? The physics is done. 10 Newton force, mu is 0.3. What's the normal force in this case?
Normal force?
Yeah.
20.
How do you know? You just said 20 and you don't know?
I'm not sure. Maybe the normal force equal to the weight.
Right. So we have our steps, right? So like it's not accelerating up and down, right?
On the vertical.
Right, in the vertical, right.
Accelerating, so the weight's equal.
Right. So yeah, we can say Newton's first law in the up and down direction, normal force and gravity have to be equal. Yeah. So since gravity is mg, 2 times 10, normal force is 20 also. You were right. I just want to make sure you can explain why you think that, right?
I just think weight.
Yeah.
Equals to normal force.
You'll see tomorrow when we do more practice, that's a dangerous thing to remember, right?
I'm not sure about it.
Yeah. And so now
I'm not clear about the whole weight process.
yeah. That's why like I want you to say it, every now and then so we can remember to do that thinking. All right, so this number 10 minus 6 is 4. 4 divided by 2 is 2. Here's another one. And I'll ask you guys to do this one yourself. I'm going to start by drawing a picture, but your free body diagram like that?
Not exactly, I think.
Well, what should you do?
I think, I noticed the length of the arrow.
The length is not. I'm not considering length. But yeah, why do you think the lengths are wrong here?
Because it's at a constant speed.
Right. So there's a key here that some people miss. Right. It says it's moving at a constant speed, and so that means we should be applying Newton. Yeah. First law. Yeah. Right. Things at constant velocity or at rest both have 0 net force. We could say our right forces equal our left forces. So what's the answer?
0.167.
0.16. That's what I got too. Yes. I'll send this in the group chat, and I'm going to stop recording now because, we're done. Thanks.